Hello, I'm Anthony. And this is joint work with Robert, Richard, and Phil. We are at Caltech. And this title suggests random product formula concentrates. So we're going to talk about digital simulation of quantum dynamics. Given a target Hamiltonian, we're going to compile it into a sequence of universal gates. Since these gates are discrete, we're going to tolerate for some finite accuracy. And we're going to minimize our gate count for this accuracy. And notice that there's some choice of metric here. We're using the spectral norm for simplicity. And notice there are also different cost model you could think about. So just to give a warning, if you actually want to get these numbers correct in realistic settings, you have to do a lot more work. And here, we're just going to use the simplest ones that hopefully captures most of the stuff. Okay. Let me also review the existing methods. So in fact, product formulas is one of the earliest ones. So all it's saying is that the exponential of sum can be break into products of individual terms. So you can also do this in other ways in higher orders, but the idea is roughly just this. And there are also different methods that's totally different. That use this control gate, this ancilla, amplitude amplification. And for today, we're not really going to talk about any of them. I just want to mention they exist and they're also pretty competitive. And today we're going to stay focused with product formula. And the reason being that they turn out a lot better than we have expected. So once you put the correct problem constraints, whether that's input state knowledge or the structure of the Hamiltonian, you get actually very, very good and very competitive bounds on the performances. And turns out they're quite comparable with these other methods. And product formula has even a better feature, at least for near term, that it does not need any of these control gates. All right. And today, the direction we're going to explore is about randomization. These authors realize you can use a quantum channel to simulate a unitary. In contrast, all these other methods, they're using a unitary. Okay. And by using randomization, there seems to be some interesting thing that's kind of only possible via randomization. And we're going to understand that a bit more today. And we're going to study instances of these random product formulas. So there's no mixing. These are all still unitaries. And turns out in this context, these high-dimensional effects or these high-dimensional probability tools come up very naturally, such as matrix concentration and martingales. And we'll see them show up very soon. Okay, let's start reviewing some relevant backgrounds. So given the Hamiltonian as a sum of few simple terms, okay, so you should think of these guys as a few-term poly. A product formula is going to simulate the ideal evolution using product of individual terms. Each of these terms, okay, is going to be simple. So one of them come here, and you're going to choose what time to evolve for. And usually it suffices to approximate a short time evolution, and you can get long time by just repeating it. Finally, we're interested in the cost in terms of gate count. Okay, so this is not exactly in terms of the universal gates. Okay, so we're just counting these. And to turn to a universal gate, you just have to multiply by some factor. Okay, and we're just going to drop that factor, okay, for this talk. And let's just look at this simple example, the first order formula. And it will also be nice that we're going to contrast it with its randomization. Okay, so let's start with the Hamiltonian, which has 3 terms with some strength lambda. And the first order formula is just going to cycle through each term. Okay. And it doesn't really matter what the order you're doing it, the bound is insensitive to it. And all that matters is that each of these terms showed up once. And it's just going to cancel out the leading order term in this Taylor expansion. So you're going to have the second order error. And that's reflected in the final gate count. So you can imagine in this higher order construction, you can make this higher and higher order, and eventually it translates into a gate count that's almost linear in time. Okay. However, you're kind of stuck with this L. So what is L? L is the number of terms in the Hamiltonian. So it is equal to 3. And it persists just because you have to cycle through all the terms. You have to put all of them down. Okay. And turns out this is quite a big problem when L is very large, such as in this quantum chemistry model or when this K-local models. Okay. In some sense, this curse of L dependence is the reason why people start thinking about randomization. And qDRIFT is invented, okay, so that it does not have an L dependence. Okay. So this is the gate count, very nice. And qDRIFT is a randomized algorithm, so it's a quantum channel, and it's going to sample each of these terms by importance. So each term is going to be sampled proportional to its strength, and when it is sampled, it's going to be evolved for a rescaled time. Rescaled such that each of these terms will be of equal roughly the same strength, and also such that an expectation is going to approximate the evolution up to second order error. Right, so you see that these two methods they cancel out the first order term using different methods, and on the left you pay a price of this L dependence. You have to cycle through all of them in one sentence. However, in qDRIFT, it only takes one term. Okay, so that's really the origin of this L independence. However, qDRIFT is a quantum channel. Sometimes that's a bit mind-boggling. So we have to not only we have to do this quantum channel. Okay, it will also be nice that we should think about this in the picture. So this is a block sphere in the Schrödinger picture. And all qDRIFT is doing is going to sample these states. Okay, so they are pure states. However, when you consider channel, all you have access to is really the mixture. Okay. So now the state is no longer pure, it's mixed. However, it somehow gets closer to the ideal evolution. You can roughly trust these geometric distances. And the formal statements are included in this mixing lemma. So anyway, this is one philosophy or just this illustration. Let's see how it goes in practice. So let's compare qDRIFT with the state-of-the-art Suzuki Formula with commutator scaling. So you immediately see that qDRIFT has a quadratic dependence on time. So that's not very good at late times. Okay. However, at short enough times, when L is very large, then qDRIFT may have an advantage. Okay, and let's see this in examples. So in local systems, qDRIFT doesn't work very well. Okay. However, when you turn on interaction, okay, so here the middle cases are power law with exponent alpha. And in this long-term regime, in this long-term extreme of SYK model, this L dependence really matters. And you see that there would be some physically meaningful time that qDRIFT has an advantage. Okay, so that's very nice. This is the state-of-the-art review of qDRIFT. And we do see that in some regimes, qDRIFT is going to do better. Okay. In this work, we're going to study the origin of this advantage. In particular, we're going to ask whether mixing is necessary for the removal of L. Okay, and we're going to answer that question by studying each of these typical instances. They're pretty natural candidates. So each of these instances are already good. It means that unitary already suffice and no mixing is actually needed. However, if these instances are poor, it would confirm the mixing advantage. And either way, either results, it will be educational. Cool. And here's our main result. As the title suggests, random product formula concentrates. So if you just randomly sample a gate sequence V, it already concentrates near the unitary. And here is the price you have to pay. Interestingly, if you only care about a certain input state, then a fewer gate count suffices. Okay, so note that we're using this trace norm. And importantly, usually this trace norm and spectral norm we use interchangeably in the deterministic setting. However, in the randomized setting, this becomes very subtle, and these two notions becomes quite distinct. Okay, it differs by the order of quantifier. Okay, and finally, let's compare with the mixed channel. So there, the error is in terms of the diamond distance, and the gate count is the best. Our concentration results has an epsilon squared. And let's try to compare each of this setting in terms of these different norms. Okay, so the spectral norm in operation, it means that you will sample this gate V, and you're going to fix that one, and you're going to allow all kinds of different input states and observables. And that also includes the very bad ones. Okay, so that explains why this gate count would be slightly higher. However, if you only care about a certain input state, okay, it doesn't need to. You don't have to have its description. It could be unknown, so long as it's fixed. Okay, so long as it's fixed before you run the program, then you have this better performance guarantee. Okay, so what's really crucial here is that you cannot optimize your state after you see at a gate sequence. So there really is a order of quantifier issue here. Okay. Anyway, let's move on to the last case. In the mixed channel, you'll be allowed to use any state and any observable. However, you have to resample the gate sequence all the time. In contrast, our concentration results is all about a instance. Let me briefly mention the proof ideas. I'm going to start with the instructive example. So here is a Hamiltonian with exponentially many commuting terms. We're going to evolve it for a very short time. Okay, and this is actually quite solvable if you just evolve a eigenstate, and all it does is to attach a phase. So this might sound fairly simple. However, if you try it with Suzuki style formulas, you're not going to put down all these terms. There are exponentially many of them. However, we'll see that randomization is giving us a big advantage. In fact, it can do this in constant number of terms. Cool. And the idea is that we can just sample a few terms as an effective Hamiltonian. And it turns out you don't need that many terms for it to concentrate. So if you just call her of things, and then you see it only requires 1 over epsilon squared terms. Then there's no L dependence. That's very nice. And in some sense, this is really illustrating what randomness is able to do, and in some sense, a drawback of these Suzuki formulas. Okay, and remarkably, this derivation stays the same if you change the input state, as long as it's eigenstate. However, if you're interested in a slightly different question, if you demand this Hamiltonian to work for all possible eigenstate, then what you're asking for is a union-bound statement. Okay, you want none of the state to fail. Then, because the dimension is very large, this union-bound is going to come with a price. So it's going to come in as a factor of n, which is logarithm of the dimension. So in this commuting example, it already captures a lot of stuff in our main results. Okay, it has been very helpful for us. However, to go to non-commuting case to complete the proof, we'll have to resort to more complicated stuff. Okay, and The picture is really a drifted random walk. Okay, so each of these steps is going to fluctuate. However, it's going to drift collectively towards a target. It's expectation, and this fluctuation is going to deviate from the expectation. You may think this drifted random walk is like a fairly standard thing to do. However, since we're on the unitary group, it's not so simple, and in fact, it's new in the math literature that we have to do it ourselves. So let's sketch how the proof works. We have to call something called a matrix martingale. So what's a martingale? A martingale is a stochastic process that tomorrow, in conditional expectation, is the same as today. So these E case are conditional expectations. Okay, and a very simple example, perhaps oversimplifying one, is the ID coin tosses. Okay. Perhaps a more representative example is the gambler's strategy. So a gambler is allowed to choose whatever it wants to do, given the past. However, since the bet is fair, the expectation remains the same. So that's roughly a martingale. Okay. How does that relate to our problem? So in our problem, we're going to randomly sample a gate sequence V1 to Vn. And we're going to compare it with the ideal evolution. And it will help to subtract the drift, okay? Because it's just deterministic and doesn't really affect much. And this guy is actually what qDRIFT has originally calculated. This is roughly the same as the Steinman distance bound. Okay, so that we know already. And what's new as our contribution is to understand this random fluctuation. Right? So now it has zero mean. So we can telescope it into a martingale. So each of these decays, these differences, they has the property that, if you just look carefully, it only depends on the past. Its future is deterministic. Okay, so if you take conditional expectation, it evaluates to 0. So it actually satisfies the martingale condition, okay, since these differences are 0 in conditional expectation. So that's very nice. We can just call a very powerful concentration inequality. It's called matrix Friedman. And in fact, it's invented by one of the authors. And so let's just take a look at this bound. It has a Gaussian looking stuff. However, it's not actually Gaussian, it has a heavy tail effect. But anyway, this is roughly Gaussian behavior. And this heavy tail is really kind of common even in scalars. Okay, so this is our friend. We should not be afraid. However, what's new here in the case of matrix is this dimensional factor. So 2 to the n is the Hilbert space dimension. So it's pretty large. And this should echo with the union bound statement that we're seeing in the last example. Okay, it's pretty much the same thing. And if you just put this into the exponential, it translates into a factor of n, okay, which is the logarithm of the dimension. So that's the proof for the matrix case. For the fixed input state, things would have to change a bit. So you would stuck in state here. And crucially, you're going to change the norm. You're just going to do with this standard 2 norm. And all the derivations are similar. However, in the end, you're going to call a different martingale bound for vector martingales. And there's no such dimensional factor. Okay, and this factor of n disappears. So very nice. We kind of see this distinction of these two natural objects. It's all arising from these high dimensional probability facts. So roughly speaking, matrices has more fluctuation than vectors. Okay, so that's all I want to say about the proof. All right, let's wrap it up. Today we see that these typical samples already doing well, they concentrate near a target if you just take n to be large. However, they're still not as good as the average. It's off by a square root, which is coming from fluctuations. It's also worse by a factor of n, which is due to union bound. Interestingly, this factor of n disappear if you only consider a fixed input state. So this is the picture. I want to emphasize that it's actually fairly general. You can apply it to all random products. And let me just quickly show you an example. So in compiling, the task is to compile a given sequence of gates into universal gates. And the question is, what is the local accuracy needed for the total, the global error? And in the worst case analysis, if you just use triangle inequality, these errors accumulate linearly, which is pretty bad. Okay, it means that you have to keep the local approximation very accurate. And this is sometimes called coherent noise. And it turns out by using randomization, you can turn this coherent noise into incoherent. And there, it's kind of really similar to qDRIFT. By mixing, you make these the accumulation of error scales kind of only in square roots. Okay, so that means you can just use a coarser approximation locally, and it suffices. Okay, so it's like the square root behavior. So in this work, we also understand what's happening here. So our work would imply that a random sequence already doing some good. Okay, and our bounds would interpolate between the two. So pretty cool. Okay, and let's just have a summary. Today we're talking about quantum simulation in the context of randomized construction of product formulas. We started with first order Suzuki formulas, and there's this factor of L, the number of terms, sometimes can get pretty large. And we show that by just randomly sample a gate sequence, you can get rid of the L. Okay. And interestingly, the gate count gets better if you fix an input state. And this doesn't care, our algorithm does not care about what input state you choose, it can be arbitrary. And this improvement is only coming from the fact that we're dealing with vector, but not matrices. And this distinction is kind of subtle and it's quite unique in the randomized setting. And this is kind of not usually discussed in a deterministic setting. Okay. Finally, let's also mention that we pin down what mixing is doing here. All it does is to turn this epsilon square into epsilon. That's it. So we now have this complete picture of what qDRIFT is doing. And this automatically applies to any randomized adapted simulation. And in terms of future work, we hope our understanding would allow better designs of randomized simulation algorithms. And also, these techniques applies to any random products. And in a different direction, you can ask about de-randomization. So far, our construction is not explicit. It's only probabilistic, its existence. It'd be nice if you can construct explicit L-independent product formulas. And practically, we also ask whether there are situations that unitaries are favored. Otherwise, it seems that you can just mix, like there's no harm in mixing, it's just a broader class. So lastly, to go beyond products, we believe these martingale tools will be very helpful. And as it already did in this random Hamiltonian analysis. So that's all I want to tell you today. Thank you for being here, and I will see you for any question at Q&A.